So hi everyone. In the previous video, we have discussed about the analysis of algorithms. So we mentioned before that one way to evaluate the running time is to use the experimental approach. And to do that, we actually have to write the code to implement the code, run it in the computer, and log their execution time. Okay, however, it's not really a fair assessment of the efficiency because we need to use the same platform like the hardware and software. So for example, if your hardware has better specs than mine, then probably the algorithm can run faster in yours. Or let's say if we are using different languages and you are using, let's say, C, and that the algorithm can potentially run faster in your using your solution than mine. Okay. Also, in the experimental approach, we have to use different input sizes to test the algorithm performance. And it's most likely that we cannot cover all the possible cases. Okay, so one approach to analyzing the algorithms without implementing it is by using the RAM model. And in the RAM model, our goal is to strip down the computer, remove the unnecessary parts of the computer to analyze the algorithm. Okay, and if you remember, we only need some memory and then the input and output and the programming capabilities. Okay, so in the RAM model, our goal is to analyze the algorithms without having to worry about the hardware, like having a faster processor or more memory, and software differences, like the programming languages that are used. Okay, so what we do in the RAM model is we count the time steps of that the algorithm will take to execute. All right, and in the RAM model, so the simple operations take one time step, and then if we have loops, then we will count it as often as they run, and then also the memory access is free. But this shows an unrealistic because in reality, it is very tedious to count all the time steps. Okay. And then, so what we want to do is to ignore ignore the unnecessary details and focus only the growth of the function. Okay. Essentially, what we do is to, again, remove the unimportant things and focus only on the main components. All right. And another topic that we have discussed is by exploring the worst possible inputs, because the worst possible inputs, this will also give us the worst case running time. So it actually boils down to the idea that the structure of the input also affects the running time of a certain algorithm. Okay, so the worst possible inputs will give us the upper bound, which is the big O notation, which again, as we discussed, is just simply ignoring unnecessary details and so on and so forth. So for example, if we have this code, and then what we want to do is to count the number of A's in a certain string. Okay, so we have a count variable and we initialize it to a value of 0. And then what we do is to loop through a string and then loop through each character in the string. And if for each of the character in the string, we are going to compare it with A. So if it is A, then we add 1 to the count variable. So how do we assess for the running time using the RAM? So we have the best case as well as the worst case. So for the best case, it is 2n plus 1. So why is this 2n plus 1? Because for every character in the string, we are going to, it will take a 1 operation. Okay, so that will give you an n, assuming that the length of the string is n. And then for every character in the string, we also have to compare it with A. So that will also give us n time steps. So that's already 2n. Okay. And why is this the best case again? Assuming that the input doesn't have any A. So if it doesn't have any A, then we can skip this line, which is adding 1 to the count na variable. That gives us only 2n. So where did this 1 come from? So it depends on the implementation of the for loop. So there are some implementation wherein it loops exactly n times. But there are also implementation that it loops until the end of the string plus 1. Okay, so that the best case could either be 2n plus 1 or just 2n. Okay, and what about the worst case? The worst case is 3n plus 1. So the worst case is from having an input that are all A's, meaning the string is like A, and so on. So what happens is for every character in the string, so we loop through it, so that will take n times. And then for every character in the string, we also compare it with A, that will also give us n times. And since the input is all A's, we have to add 1 to the count variable every time. So that is already n for looping through each character in the string, n for comparing the character with A, and then n for adding 1 to the count variable. That's why the worst case is 3n plus 1. Okay, so we observe the following from the algorithm. So each character in the string is considered at most once. And for each character in the input string, a constant number of steps is performed, like 2 or 3, depending on the kind of input that we have. Okay, so if we deal with the best possible inputs, then it's just 2n. Then if the worst possible inputs, then it's 3n. Okay, so with big O also, we say then that we have this function C1 times n plus C2, which is bounded by some O of blank function. Okay, so we have a constant value multiplied to n, which is the number of character in the string, or how many time steps, plus C2. So this is just a generalized form of this running times that we have achieved here. We had 2n plus 1, for example. So the C1 here will be 2, and then the C2 is 1. But if it's worst case, then the C1 is 3 and the C2 is 1. Okay, so we can then say that we have a function C1n plus C2, wherein C1 and C2 are non-zero constants, which are contained in some function big O. Okay, but what function is it? O of what? So we say that the running time of the algorithm is O of n. Again, in the big O, if you remember, we simply have to discard all the unnecessary details, like the C1 as well as the C2. Okay, and we will be left with n. Okay, so we say that the running time of the algorithm is the O of n, or also the linear na time. So what about for this one? For this kind of problem, what is the running time? What will be the running time of this algorithm? So we have discussed in the previous slides, or the previous na discussion, that if we deal with a double loop, or nested na loop, then it will be a quadratic quadratic function. Okay, or O of n squared. Why? So let us look at the source code again. So we have result equals 0. So essentially, this is 0 since we are just doing a memory access. And then for the first loop for I in 0 to n. So that means that we are going to loop n times. And then for each value of I, we are going to have another loop for j in I to n. Okay, that means that this will take n times and this will take n times, and you multiply that, that will give you n squared. Okay, and then plus n actually. So this will give you n times. Let me just write it down, annotate it. So, oops. Let me just draw. Okay, so this will give you why cannot I draw? Okay, so this will give you n times. So for example, if you have 0, 1, 2, 3, and then this is for the value of I. And then for 0, you are, let's say, the I here is 0. And then for each of this, say 0, 1, 2, 3, and then for another, for 1, this will also run for 0, 1, 2, 3, let's say 4 times. So this will give you n squared, and then this result equals 0, result plus j. How many times this will take time? This will take. So this will be n squared. Okay, so since you have to loop through n, and for each value of I, we are going to loop through the n again. Okay, so that will give you n squared plus n squared, or 2n squared. Okay, and we simply have to discard some details or the constant, so we will be left with O of n squared. All right? Okay, let's move on. How do you erase all of this? Sorry, Zoom, I'm a noob. Okay, I will teach you more about this later. But for now, let us move on. Okay, so technically, O of n cubed is also correct because n squared is less than n cubed. Okay, but what we want is the tightest bound, which is O of n squared. Okay, so that means that this algorithm can also be bounded by n cubed, or n raised to 4, or n raised to 5, or 2 raised to n, but we don't want those functions. Okay, what we want is the tightest bound, which is closest to our approximation, which is n squared. All right, so we already went through this example before. I don't want to repeat this anymore. So essentially, we just had some exercises. So which one of the two is better? So the easiest way is to just look for the dominant terms. And for here, the dominant term is n cubed. And then for the right, the dominant term is 100n squared, which has a big O of n squared. So since n squared is lesser than the n cubed, then this function on the right is also faster. Okay, and we also look here at the asymptotic na graph of the two functions, wherein the red line is the n cubed plus 2n squared, and then the blue line is the 100 squared plus 1000. So the x-axis is the input size, and the y-axis is the running time. And as you can see, as the input size grows, then the running time is also growing. And we can see that initially the n squared actually has higher running times for some input sizes than the n cubed. But after some point, let's say here at input size 100, we can see the obvious na growth of n cubed compared to n squared. So we can then say that this O of n squared is better. Okay? And what about for this one? You have n raised to 0.1 times compared to log n, which one would be faster? And essentially, if we just use the order of growth of the functions, then the log n will win, right? The log n will be faster. And if we look at this graph, initially at some point, this red line, which is n raised to 0.1, is actually faster compared to log n. But after some point, like let's say this input here, midway, we can see that the log n is getting faster compared to n raised to 0.1. So we can then say that the log n is the winner. Okay, so what about this one? We have 5n squared versus n factorial. And it's very obvious, we can see here on the graph, the n factorial, which is the blue line, is so much slower compared to 5n raised to 5. Okay, especially when it started on between 9 and 10 inputs. Okay, and the running time for n factorial just shoot up compared to the 5n raised to 5, which is a tad faster compared to the n factorial. Okay, and what about for this one? 8 raised to 2 log of n base 2 compared to 3n raised to 7 plus 7n. So for this, what we can do is make use of some logarithmic rules, and we can simplify this function. Okay, so if we have 8 raised to 2 log of n, so we can make use of this logarithmic rule that if log of m raised to n, that will be equivalent to n times log of m. But we can also use it the other way around. So if you have n times a log of m, that can be equivalent to log of m raised to n. Okay, so essentially what we did here is we used this rule of logarithm. So we then have log of n raised to 2. So this 2 here, essentially the n was raised as an exponent. Okay, and then we already have this. Then we can further simplify it. The 8 may be converted into 2 raised to 3 because they are equivalent. And then we can simplify. So it will be 2 raised to 3 log of n squared. And we can make use of this third log rule again. The log of m raised to n equals n times log of n. So that will be, this 3 here will be raised as an exponent to n. So that will give you 2 times log of n raised to 6. Okay, and then using this rule, so a raised to log of n base a, if they have the same base, so that will be equal to n. So we just brought down n raised to 6, since we know that the base of log here is 2 anyway. So this is equivalent to n raised to 6, and n raised to 6 is so much better compared to 3n raised to 7 plus 7n. So we can then say that this function 8 raised to 2 log of n base 2 is faster. Okay? Now, in the next video, we are going to discuss each of this one, the big O, the notation, then the and big O notation, and then followed by the omega, big omega notation, and the theta notation. So the big O notation is the asymptotic na upper bound, and the big omega is the asymptotic na lower bound, and the theta notation is the asymptotically tight bound, which is used to describe the average cases. Okay, so we are going to discuss each of these in the next video.